This slide set is about the Internet Protocol version 4. However, the first slide shows a general view on the current situation, which also holds for version 6. On the left side you see the different layers of the hybrid model, and on the right side there are protocols which belong to these layers. I will not go into the details of the protocols in this video because I would like to highlight the importance of the Internet Protocol. You can see that there are many protocols on the physical layer and on the data link layer. On the application layer there are even more protocols. In contrast, in the network layer there are just the Internet Protocol and helper protocols such as routing protocols, ICMP and IGMP belonging to it, but no alternatives. This means that a convergence has happened so that the Internet Protocol is used everywhere. You can also say IP over everything and everything over IP, which means that IP can be combined with all data link layer protocols and all protocols on higher layers. This convergence is useful so that all computers can communicate with each other. IP version 4 has been introduced in RFC 791 in September 1981 as the network layer protocol for the Internet. It is a connectionless protocol, which means that each IP data unit is independent from previous data units. Another core feature is that it is unreliable. There is no guarantee that an IP data unit reaches its destination. This is also called the best effort way of operation. Data units are called IP packets or IP datagrams because the Internet works based on datagram switching, which is a typical way of packet switching. In the figure we see what is happening inside of a router when the router processes an IP packet. Before we go into the details, it is necessary to mention the terms control path and data path. Control path means that packets are sent for management purposes. So there are packets which do not contain user payload but control data to make sure that the network operates in a reliable manner. On the data path we have packets which contain user payload. In the Internet, control data and user data are sent on the same links, which is called inline signaling. The alternative would be out-of-band signaling, where additional links exist just for control data. In this figure we focus on what is happening on the data path. At first there is the IP processing, which means that the contents of the IP header are examined. The IP header contains a checksum, for example, so that it is verified that there are no bit errors. Afterwards, a route lookup happens where the routing table is accessed. Based on the prefix, that is, the beginning of the IP address, it is decided which router port is used to forward the IP packet. The routing table is sometimes updated based on events in the network, such as link failures or information exchanges with other routers. In the following, there is the possibility to classify the packet because the provider may decide that some traffic should be preferred over other traffic. For example, a provider would like to prefer voice over IP traffic in relation to backup traffic. There is no general agreement how classification has to be done, so that every provider can configure it on its own. At the end, we have 3 waiting queues here, where each waiting queue has a different priority. I'm assuming a strict prioritization of the waiting queues. If there is at least one packet in the highest priority queue, then packets from this queue are sent. Only if the queue is completely empty, then packets from the second queue are considered, and only if there are no packets in the first or second queue, then packets from the last queue are sent. Now we take a look at the structure of IPv4 packets. The packet consists of the header and the payload. The minimum header length is 20 bytes. Often it actually has this length because options are seldom used. At the beginning the version is indicated so that we find a binary coded 4. since there can be options. The length of the header is specified in the next field. However, the common value in this field is 5, which shows that no options are used. Then there is the field type of service, which has been renamed later to differentiated services code point. The idea is that different types of traffic can be indicated here so that they can be treated differently on the routers as explained on the previous slide. At the end of the first row, we find another length field which shows the length of the complete IP packet. It has 16 bits, so that a maximum length of more than 65,000 bytes is possible. It is, however, often not useful to work with long IP packets due to payload size limitations on the data link layer, which would then lead to IP packet fragmentation. The next row contains fields which are needed to control such a fragmentation. Please refer to the video about fragmentation to understand their meaning. In the third row, there is the time to live field. The original idea of this field was to specify a maximum time that it may take to reach the destination. If the time was exceeded, then the packet would be dropped. However, the actual meaning of the field right now is that it indicates a maximum number of forwards by routers. The value in the field is decreased by every router which is traversed. If the value reaches 0, then the packet is dropped and an error message is sent. The TTL field is in particular important for misconfigurations where routing loops exist. So a router A may send a packet to router B sends it to router C, and router C sends it back to router A, and so on. Please note that the TTL value is only decreased by routers. Switches do not process the IP header at all and therefore also do not change the TTL value. Switches are therefore invisible from an IP point of view. The next field is called Upper Layer Protocol or short protocol. This protocol is a transport layer protocol which is used in the payload. It is necessary to indicate the protocol because it would otherwise not be clear how to process the payload. Common protocols which are indicated here are TCP, UDP, but also ICMP. Afterwards, there is the header checksum. Its calculation is relatively simple and is basically a summarization of ones. The checksum relates only to the header. It has to be changed on each router because the TTL field is always decreased. At the end of the header, there can be options. For example, options may influence the path by specifying routers which have to be used along the path. Finally, there is a payload.